Hello guys, welcome to thermodynamics online tutorials. On today's episode, we'll be discussing on the second law of thermodynamics and some of its examples. Welcome back. So now on today's video, we'll be discussing on majorly examples, and on this video I'll be giving out formulas you're using to solve any thermodynamic question, any of them. So now let us start by writing out some of the work done in some processes, in some thermodynamic process. Now for the start, we have the work done. I think this is finished. Now we have the work done in a polytropic system. Polytropic process. Now we say the work done is equal to what? P2 V2 minus P1 V1 over what? 1 minus n. We also have work done in the isobaric process. In an isobaric process, we say the work done is equal to what? P V2 minus V1 is for an isobaric process. And we know when we talk about isobaric process, we know that the pressure is what? Constant. But in a polytropic system, we said that the heat is what? Constant. That means the heat is not changing, the heat is constant in the process. So now we talk about work done in an isobaric process. When the volume is constant, you know that work won't be done because it is not moving, there's no work done. So our work done in an isobaric process is equal to 0. And when we talk about an isothermal process, you know that the Q will be equal to 0. So our work done is going to be negative of what? Negative of the internal energy. So now let me give this relationship out. It will be needed, it will be useful in your solving of thermodynamic problems. Now n minus 1 over n, which is equal to v1 over v2 raised to power n minus 1. You can use any of this relationship to get your p2, p1 or v2, v2 or t1, t2. So let us talk on internal energy. When we talk about internal energy, we'll just be giving out some formulas in this video. Now the internal energy is respect to CV or M or R or any of those constants you'll be given. So we have another one, we see changing. So this is for work. Now when you are given the work, we say work is equal to R T2 minus T1. I'll suggest you write this down. I'll suggest you write these formulas down. They'll be useful. So we also have work done in polytropic system in respect to mass. When we are given mass, we have m T2 minus T1 open bracket n minus 1. This one is for a polytropic system. We also have work done equal to m RT ln V2 V1. This is for an isothermal process. So now all these formulas I've given you, I would suggest you get it, you write it down. And I'll also be giving some of these formulas you'll be needing also. Now, let me just open your mind to when you talk about when you are being asked to calculate the total work done or the total mass. We know that when you are being asked to calculate the total work done, it can be W. Now, the total work done can be equal to the work done of the piston, or let us say something like that. Work done of piston plus, let's say in the piston paddle system, work done of piston, work done of paddle, or something like that. When you're talking about the work done or the total work done, you just have to add all the works together to get your total work done. When you're talking about your total volume, you have to just add your volume together to get your total volume. With this, let us dive into our first question for the day. So our question says a piston cylinder assembly contains what? It contains what? 5 kilograms of air. The air is compressed polytropically with n equals to 2 from an initial state where the temperature is 127 degrees Celsius and pressure of 1.5 bar to a final state where the pressure is 4.5 bar. Assume that the air behaves like an ideal gas. Determine the work done and the heat transfer during the process. We know that for air, our specific capacity for pressure is equal to 1.0034, and specific capacity for volume is equal to 0.7165, and our R is equal to 0.287. So let us dive right into the question. Now, the questions that we are given, we have to get down some assumption. We have to write down some assumption, because these assumptions can be useful, even if it might not even give much marks in the exam hall, but I think it's needed to write it down. So now the first assumption we have is that the air is a closed system. What does that mean? It goes in, comes in, goes in. So we know that this is a closed system. We'll write that down. Our assumptions. Our assumption 1, the air the air is a closed system. We have assumption 2, the process is polytropic. The process is what? The process is polytropic. To show you that the heat was what? Conserved. They said the process was what? Polytropic, with index n equal to what? 2. So now we have 3. We said the air behaves what? The air behaves as an ideal gas. Air behaves as an ideal gas. So now what we need to do is that, first of all, the temperature we are given is not supposed to be in degrees Celsius, it's supposed to be in Kelvin, because this we are doing an ideal gas here. So now at state 1, let us write that down. At state 1, our P1 is equal to 1.5 bar, and our T1 is equal to 127 degrees Celsius. If you add your add it plus 273 Kelvin, now we have it to be 400 Kelvin. Let me clear this so it won't interfere with what we are writing out here. To go to 400 Kelvin. Now at state 2, our work done, our P2 is equal to what? 4.5 bar, but our T2 is what? Unknown. So we have to get what? Our T2. And let us also know that we have mass also. Let me write this there. We also have mass equal to 5 kilogram. So now to get this our T2, remember that relationship I wrote here when I say T2 is equal to T1, which is equal to P2 over P1. I will suggest you memorize this, which is equal to V1 over V2 n minus 1. Now what are we looking for? We are looking for what? T2. We have P2, P1. So this is what we just make use of this. Let's make use of this one here. So we have T2 over T1 equal to P2 over P1. So what we are looking for is our what? T2. So we say our T2 will be equal to T1 P2 P1 n minus, which is now equal to 400 P2, which is equal to 4.5 over 1.5 n, which is 2 minus 1 over what? 2. Solving that, we have 692.8 Kelvin. So we've gotten our T2. Let me clean this part. The board is small. Just take it a bit. Just take it here. So now demarcate this. So what we want to get now is what? What were we asked to get? Let us go back to our question. What were we asked to get? We were asked to get what? Now assume that the air behaves as an ideal gas. Determine the work done and heat transfer during the process. So what we are looking for is what? Work done. We are looking for work done, and we are looking for heat transfer, which is Q. This is what we are looking for. We're looking for. Now let us get our work done. We know, if you remember when I was giving out this formula, I made mention of W equals R open bracket 2 T2 minus T1 open bracket 1 minus what? N. Now getting our work done. Now we have know our R is equal to what? 0.287 open bracket T2 which is 692.8 minus T1 which is 400 over 1 minus N which is equal to what? 2. Now when we solve this, we will have it to be what? In kilojoule per kilogram. But what we are looking for, we want to leave our answer in what? Kilogram. So let us find something that can cancel this kilogram, and that is the 5 that we have here. When we have 5, let me bring this out. When we have W is equals to 5 kilogram, this kilogram cancels. Sorry, let me write it down. This kilogram cancels this kilogram. So when we, let me clean this. So when we do the mass there, we have our W to be equal to minus 420.17 kilojoule. 420.17. Now we've gotten that. Now the light is out. So now we want to get our what? Our Q. We've gotten our W, which is a negative. So that means what this tells us is that heat is what? Is going out of what? Out of the system. So now to get our what? Our Q. Forget that. Now let us use this formula. W equals. Sorry, this is not the formula. Let me write it out where Q minus W is equal to change in what? Change in U. So now solving, changing. Now we've gotten our W. Now what? Let us get our change in U before we get our Q, because we know how to get our change in U by when we have CV or the rest or something like that. So now to get our change in U, we say it is MCV open bracket T2 minus T1. If you remember the formula I gave out earlier, which is equal to what? 5 times 0. Now this M that is here is to cancel the per kilogram that we have. Hope that is not confusing. Open bracket T2 which is 692.8 minus T1 is equal to 400. Let me take it off. Yeah. So now we have it. Now we have our change in U to be equal to 1048.96 kilojoules. So now after we've gotten that, now what we want to get now is our Q, which is the heat that we've all been waiting for. We have W plus change in U, which is equal to minus 420.17 plus 1048.96, which is equal to 628.79 kilojoule. So now this heat is absorbing into the system and the work is done by that system. So now with this being said, I will leave a comprehension. I'd like you all to try that out and leave some of the answers, or most of the answers in the comment section. Bye bye for now.